I'm here.
Cool. So I'm stop sharing the screen. Stage is yours. You are our star. So come on.
Thank you so much. I am coming to you from Las Vegas on a little trip. I don't have my normal presenting setup, let's say. So bear with me a tiny bit here. But hopefully you can see the slides.
Yep, we can.
Cool. Okay, so someone can mute. Okay. So thank you so much for having me, Tomas and Philip. My name is Paul Singman. I'm a developer advocate at an open source versioning analytics project called lakeFS. And we're going to talk today about optimizing object stores for data analytics and other type of data work with lakeFS and some other technologies. Let's get right into it. So the agenda for today is going to follow a pretty straightforward narrative of first talking about why object stores are so popular and great in a number of ways, but also then touch on two ways that they can and have been improved for data work that will fit somewhere in that nice diagram Tomas showed earlier. The first optimization is called modern table formats. Common examples are listed. And the second is an even newer concept, which doesn't have a solidified name yet, but I like one way I name it as data source control. And then we'll finish up with a demo of both optimizations working over an object store. So we're going to start with a confession, which is that I love object stores. We're talking about for the most part, the object store offerings, the major cloud providers that you can see here, including MinIO, an open source alternative. And I love them because they're awesome in terms of these characteristics: performance, cost, the developer experience, and they're very easy to connect to a whole wide range of tools. From my experience, what I've seen, they've become extremely popular for a wide variety of use cases, and we almost sort of take them for granted in some sense. So I think it's worth it to dive into some of the impressive characteristics that they have. The first is performance. Most of my experience comes from using S3. It's where I've pulled a lot of these stats and metrics from. It's super easy to get a great performance, reads and writes per second. It scales automatically, and it's pretty much always available despite some notable AWS outages in the past couple months. When comparing to block storage, object storage is typically 5 to 8 times cheaper when it comes to the two things you'll be charged for, which is the storage itself and the network requests you make to access or store the data. There are mature client SDKs in pretty much every language to connect to them. There's no like JDBC kind of clunky protocols involved. It's pretty much simple HTTP requests. Object stores also offer a lot of features beyond the basic storage itself. In the past year or so, for example, AWS has offered a strong consistency of reading files after writing it. It's guaranteed to appear, despite being a massively distributed system. And one storage lens is a new feature that out of the box gives you nice ways to visualize your usage and optimize costs and stuff like that. You can set up event notifications, very granular prefix level permissioning. most people, I assume, are somewhat familiar with all these features, but if you haven't really dove into everything that's offered in S3, there is probably more than meets the eye. And lastly, the S3 API, for better or worse, is somewhat of a standard for communicating with a whole range of tools, whether it's a data warehouse like Snowflake or Redshift, or Kafka, or a query engine like Spark or Presto. They all speak the object store language and make it easy to move data, put it in and out of an object store. So, I forget this, but lakeFS, that's our logo. We are very connected to object stores and directly built on top of them. So the question remains is how can we improve upon them if they're so amazing? And it is the case, though, that we can, particularly when it comes to doing data intensive work, analytics type work. There are a couple things we can sort of add above the object store layer to enhance them. And the first optimization are what are called modern table formats. The idea for these are to maintain essentially transaction logs, or what are called manifests sometimes, as metadata stored alongside the data itself that query engines can use to make use of, to provide additional guarantees to the data. The three most common implementations of this are Databricks' Delta Lake, Apache Hudi, and Apache Iceberg. So the concept is pretty straightforward. You can see in this diagram taken from the Delta Lake blog that for any data you put in the object store, here you have a Parquet file, two Parquet files. A Delta transaction log will exist alongside the data, and in a very granular way, keep track of which files have been added and deleted. And this provides some pretty basic but important guarantees when working with data. When people initially started using object stores for analytics work, they would run into some honestly silly issues of what happens when reading a file as one is being written. And you might get sort of funky results because it's like half of the data has been written, or you might see a query error and just have to retry, which is kind of annoying. So this lets you write data without it affecting reads. You can traverse this log to provide some basic data versioning and get other performance improvements. Modern table formats are, they're in like year 2 or 3 of their existence and are pretty popular, becoming they have a stronger ecosystem around them, being integrated with other tools, and I foresee their usage only continuing to increase from here. Whether all 3 will stay popular or one will sort of win out is sort of up for debate. But it is good for the community to know that these formats are available and make your data in object stores a little easier to work with. Next, we'll come to the category of data source control. And the idea here is to extend the operations available to you in an object store with something like those available to you with Git and managing code. This provides a number of benefits that we'll cover in more detail in a bit. But it helps you fix data errors and update data sets more simply and with development. lakeFS open source project and Project Nessie are 2 main examples of technologies that are implementing this idea. And one way that I like to visualize it and make this more clear is to think about the objects. Think of an object store's interface, like S3, for example. And I took the screenshot here to show you which operations are available to you over the data you put in it. So we can copy a file, we can move a file, we can delete a file, and that is to some extent what we're limited in doing with this data. However, it would be pretty cool, would it not, if there were a few other buttons here that we could do, like take a commit of our data set, maybe create a branch, multiple branches off this data set, and then perhaps merge them back together via pull requests. And this is essentially what lakeFS and Project Nessie are allowing to happen by behind the scenes managing metadata about the files. So here's a screenshot of the lakeFS UI, and you can see it's essentially a combination of something like an object store and GitHub, where we have our data listed in the same way, but also tabs available for taking commits of the data, creating branches, and eventually comparing them and merging them. So it's a pretty cool idea, one that isn't so simple to implement in a scalable way to meet the scale of potentially gigabyte, petabyte size data sets, but one that we have managed to do at lakeFS. So I want to make it more clear how these Git operations let you more elegantly manage your data and get these benefits. So I'll start at the top. If you have a data error, make it into production. There's something you need to fix, fire to put out. Without data source control, you might be deleting files in a partition and then rerunning a job. And this can take minutes, it could take hours, depending on the size of the data. With the lakeFS command line tool, you can simply run a one-line revert command and roll back the data to a previously known good point in time while the issue is resolved. For updating data sets and object stores, you might add the new files to one location and then copy them over to the main location where other consumers are reading. But in this, with these operations available to you, you can create a branch, add the new data files there, and then merge them back into the main data set where they are exposed atomically in a very elegant way to different consumers. Developing an isolation with object stores typically involves copying data, a subset of the data to like your own personal folder, or ETLing data around. Here we have a really elegant way to create a branch and instantly get a copy of the data without actually duplicating it, where we can test different changes and do whatever we were considering trying to do or experimenting. And we can, again, merge the data back in at the end or simply delete the branch. If you want to know finally, if you want to know what the state of your data is at a particular point in time, every time you take a commit, which you can do whenever you want, you can use the generated commit ID to point to the state of not just one data set, but as many data sets as you manage with lakeFS to the given commit ID. So that is a bit more detail on how this works and gives you these benefits. I'm going to hop now into a demo that shows both of these optimizations for data lakes in action. Before I do, though, I will open it up for questions if there are any that someone wants to ask at this time.
Yeah, maybe I will start because we already talked about it. Cloud. So Is it available only on one provider, or it can be used only on bare metal server, or it could be like the private cloud, like OpenStack or any other?
Yeah, so lakeFS is it's purely open source at this point, although a managed SaaS solution is coming. So you can run it on a private server. You'll have to manage that installation yourself, of course. Yeah, it can run on top of any object store, and it is available as can be run via a Helm chart with Kubernetes or in a Docker container, or you can install it from source and connect it to whatever object store you're using.
Good, thank you.
Thank you. So, okay, we'll hop into the demo here, and then definitely have time for more questions. So I have two tabs here. One is the UI of an installation of lakeFS. We have 2 repositories, each pointing to different buckets in S3. We're going to use this my awesome repository for this demo. And you can see that it has no data in it at the moment. What we're going to do is use a Databricks notebook that is configured to via just a few environment variables to talk to this lakeFS installation, so that in the same way you might read and write data to an S3 bucket or some other object store bucket, it'll instead go through our lakeFS installation. So Databricks comes with a few, actually more than a few, data sets just available. And we're going to use one of them, which is comprised of Amazon reviews, which we can easily load into a data frame just by pointing to the right path. And we can show what this data looks like. But ultimately, we are going to save it to our lakeFS repository. Here you can see some of the data here, just for curiosity. And we're going to save it to the lakeFS instance. So the repo name was my awesome repo, which basically has a one-to-one mapping to the S3 bucket. So when saving data to an object store, you're typically using the S3 path, and it looks very similar with lakeFS, but you have a repo name, you have a branch name, and then you can do whatever directory structure you want to. So nothing fancy going on here, but we're saving the data. By default, Databricks at this point uses Delta, the Delta format. That was one of the modern table formats we discussed earlier. So in our repository, we now have this Amazon reviews folder, and the data is in an uncommitted state, but you can see the data files here and the Delta log files here. And we can commit them in the repository, and just give us a nice, checkpoint the data here. If we want to change it, we could go back to the previous state using the commit ID when there was no data. And what I want to do is show the workflow for updating this data set in a way that is less error prone and than a typical way you might update data in an object store. So the way you start is by creating a branch. Ours is called, let me just get the name here. We're going to call it fixed time column. We could call it anything we want, similar to the way you might name branches using Git for code. You could maybe adopt some conventions, but the name is just a human readable name. And you can see in the data set here that we have this pretty ugly time column that I certainly doesn't know what it means. So let's update it to be a more human readable format. So here's some Spark code to do this. We're creating a new column review date, which you'll see has a much nicer looking time column. And it'll be here on the end, but it's better in my opinion. And what I want to do is now save this data frame, aligning the columns. That's what some of this code is just doing here, just readjusting the columns we have. And we're going to, again, nothing complicated, but save the data again, this time pointing to the fixed time column branch, which will end up here in the path we save it to. So that's running. If we go back to our repository, we can now go on to the fixed time column branch, see that there are new uncommitted changes of data we saved. If we go back to the main branch, we see that the changes don't appear there. So we have good isolation between the branches. The main idea is if we have data consumers reading from pointed to the main branch, we can experiment with these changes on this branch without worrying about how it will affect them. So we'll commit these and now simply merge it back into the main branch via like a pull request. And sort of voila. Now on the main branch, this fixed time column will appear and any consumers reading this data will now see the change. And we can read in the main branch again and just see that the change took place. Here we have our review date column instead of the original time column. So that's the demo. Pretty simple, but I think it hopefully showed you some of the main operations you get available to you when using lakeFS in particular. So yeah, I'll just wrap this up with a couple notes. lakeFS is designed to handle, as I mentioned, very large scale. It is due to pretty advanced, what we call the Graveler data model that keeps track of each branch in your repository and which commits are a part of that branch, and as much as possible, reusing these range and meta range sort of objects that keep track of which files are contained in each commit. So if between two commits, pretty much none of the files change, for the most part, we won't be duplicating data, but simply adding pointers to the different meta ranges to keep track of the files. And this lets us achieve great scale. lakeFS is format agnostic, so whether it's Delta files, as we've shown, or CSVs or Parquet or anything else, it's all the same as far as lakeFS is concerned. And it was sort of an architectural decision to design it to sit at sort of the infrastructure level of your data lake. We expose a subset of the S3 API. So any tool that knows how to read and write from an object store like S3 can very simply read and write from lakeFS, as we showed in the demo of just changing the path to point to your repository name and the branch name. So
we have one question. can lakeFS now do comparison between branches, like values in columns of data that have been changed? Yeah, that's something I wanted to also ask, if we can check it in, for example, in UI, that the difference between data.
Yeah, that is a good question, and it doesn't work on the data level. Oops. So yeah, so to answer that question, it is purely on the object itself, and like, you know, a hash of all the values in it. So it will know that something changed, but it won't know what the change is within the data set or object itself. Something that has been you know, discussed, something you can kind of, I haven't, I guess, really proved this out, but maybe use something like Delta or one of the table formats in conjunction with lakeFS to identify which objects have changed, and then more granularly go into those objects and see what the changes were. But for lakeFS, it's all objects in a object store.
And if we have file, for example, JSON, can we just open this from this UI? Or this is just object with hash, and that's a black box from UI perspective?
You can download the object to your local computer and view it there, but you don't you don't see the data itself from the lakeFS UI. It is meant to, you know, you can still use whatever database or query engine to actually transform and crunch the numbers.
Okay.
Any other thoughts or questions?
Yeah, I have a question. So maybe like big picture or some overall. So can you give an example that real use cases when file FS will be useful or will resolve some technical problems? I mean, some real example where we can use it.
Yeah, lakeFS. Just to make sure you have the name right, but we see probably our two most popular use cases that we have of users of the project are, one is the using branches to create development environments that are exact replicas of your production data, is something that people are pretty simple, like beginner use case that people are adopting to their workflows. Another example, which may be a little bit more in the spirit of your question, is we have a fair amount of machine learning teams using us that care a lot about reproducibility of experiments, and keeping track of what the exact state of a data set was that was used for training a model might involve, for the most part, will involve like making a copy of the data, maybe like hard code saving it to a bunch of different places. They like the ability to take commits over their data sets, and then in a much more simple way, just say like, this was the commit ID used for training this data, and these three data sets were in this exact state as of this commit. So we can you know, reproduce our experiments more simply in this way.
Okay. Do you think is there any chance to replace HDFS by lakeFS?
So, I mean, for the most part, if I understand the data world correctly, object stores are something of a replacement for like the Hadoop file system. So would you agree with that?
Yeah, I think.
Okay, so lakeFS is certainly a bet on the continued adoption and user experience around object stores and their use in big data type work. So you could definitely think of it as a replacement for HDFS. And it's certainly a trend that most people agree is happening, albeit how fast, but like a replacement of the entire Hadoop ecosystem is certainly underway, but maybe accelerated by tools like lakeFS and the like.
Okay, thank you. So another question from chat. What are the main directions in which you want to develop lakeFS functionality?
Yeah, so a big one that we have planned later this year kind of goes along with the replacing HDFS theme, which is we want to, so a lot of people, some users are hitting friction when it comes to like the Hive meta store in particular. And with lakeFS and the concepts of having data sets on different branches can appear messy, whether you're using something like AWS Glue or Hive Metastore. You're kind of creating, it would be nice if those tools could become, as we say, like more branch aware. So we do have it in our roadmap to develop our own Metastore as a replacement to the Hive Metastore. We've published a couple of pretty popular blog posts explaining the issues with Hive Metastore and why we think it's time that it should be replaced. So that is a big one that extends our functionality to sort of a higher part of the data stack. Otherwise, we are, maybe it's not exactly product functionality, but we're planning to launch a managed SaaS offering by like Q2 this year. And of course, there's always performance improvements happening behind the scenes and usability improvements to make it more clear, to make it work more smoothly with this technology. A lot of different tool integrations. One notable one I'll mention is with dbt that again makes it easier to use lakeFS branches and run dbt models on different branches without copying data as much.
Okay, thank you. And another question, is it Git-like or it just itself, using Git itself underneath? Just curious, that's Vitaly asking. Yeah,
it's a good question. It is definitely, as far as I understand, Git-like. What lakeFS does under the hood, as you kind of got a glimpse of with one of the diagrams shown at the end, it's doing something very different than what Git uses to keep track of the differences in files. Our solution is much more focused on the scalability of data, which is essentially the main reason Git breaks down for data. So we, for user recognize, so people understand the concepts already, we use the same terminology as Git and make them Git-like, but it is not like the same things happening under the hood.
Yeah, Git likes to scream when you try to commit 2 gigs or 1 tera the data file. So that's the difference, I think.
Yeah.
lakeFS will just take it.
Yes.
Yeah, and I would say that I mostly like your answer about the files that are used by the example, some testing by data engineers or some models, I mean machine learning models, that could be the really useful. Now I can imagine where to put in all the puzzles in data, where to put this tool. So I think the last minute, if you have any question, just shoot.